Hello everyone and welcome. In this video we will be revising the chapter which is related to work and energy. So these questions will really help us improve our knowledge in this chapter, and also we can just use it to revise this chapter if you don't have enough time, so you can go through it as fast as possible. Let's start with question number 1. It says here for questions from 1 to 3, a ball projected upward at a 45 angle from the edge of a table with an initial speed of 3 meters per second as shown next. Assume that air resistance is negligible and answer using the following choices A, B, C, or D. So question number 1 says, at which point in the path is the ball traveling at its lowest speed? At the first moment, the thing that will come to your mind that this question is about projectile motion questions. It doesn't have to do with work and energy. So anyways, you can answer it either using your knowledge about work and energy or using your knowledge about kinematics or motion in two directions. So both things will reach to the same answer. Now it's asking at which point does the ball have its lowest speed? Well, actually, we know here that the ball has potential energy because it's lifted above the ground. Now, other than that, it was given a kinetic energy equal to 3 meters per second, or sorry, the speed is equal to 3 meters per second, therefore it has kinetic energy. Now, we know the higher the object is reaching, the lower the speed, therefore the lower the kinetic energy, but what's increasing is the potential energy. The potential energy starts to increase, and we know at the highest point, the potential energy will be highest, but the kinetic energy will be lowest. So this means that the ball will have its lowest kinetic energy at point B because it's losing its kinetic energy while it's going up, and it's transforming it into potential energy. So the answer is B. Now question 2. At which point in this path does the ball have a speed greater than 3 meters per second? Well, we know that the 3 meters per second was the speed of the ball when it left the table, okay? Now, as it's going up, its speed is decreasing, but as it's going down, the speed is increasing again because we know now that the potential energy is becoming lower and there is more kinetic energy the farther the ball is going down. Now it's asking, where does it have a speed greater than 3 meters per second? Okay, now we know that we have kinetic energy and we have a velocity of 3 meters per second. Here, the vertical velocity will be 0, but it will have a horizontal velocity, but the vertical velocity will be 0. Here, the kinetic energy will be gained again. Well, we can say at location C, we will have a speed equal to 3 meters per second because all the kinetic energy it lost, it gained it again. Therefore, it will have the same speed that it had when it left the table initially, which is 3 meters per second. Now, it's asking where does it have a speed greater than 3 meters per second? So the word greater changes everything. Greater means that the speed is more than 3 meters per second. Well, we know that the ball is still falling and it still has potential energy because it's above the ground. It's still moving downwards and still losing potential energy, and it's transforming it into kinetic energy. So it's even gaining more kinetic energy than the kinetic energy it had at the beginning at this location. So we can say that at point D, it will be faster than when it was at point C or B or even its initial point. So the answer here is D. Question number 3. At which point in its path is the ball's kinetic energy equal to the initial kinetic energy? Well, we already answered that in the previous part of the question. We know that here the object will have the same speed as it had when it left the table because it has the same speed and we have the same mass, and we know that the kinetic energy is equal to half mv squared. Since the velocity is the same and the mass of the object didn't change at all, this means that at point C, it will have a kinetic energy equal to the kinetic energy when it left the table. Question 4. A 10 kilogram steel ball is dropped from the top of a tower, which is 100 meters high. The kinetic energy of the ball just before it strikes the ground is most nearly A, B, C, or D. Well, first of all, we know that the object is now 100 meters above the ground because it's thrown off a tower, which is 100 meters above the ground. So what type of energy does it have at this moment? Well, it has only potential energy, okay? And we can calculate this potential energy using this equation. PE is equal to mgh, and we have the mass of the ball, which is 10, and we have the gravity, which is 9.8, and we have its height above the ground, which is 100. So the answer in this case will be 9,800 joules. Okay, now this is its potential energy. It's asking me to find the kinetic energy of the ball. Well, we know that the object is falling down. Since it's falling down, it's losing its potential energy and it's gaining kinetic energy. So just before the object touches the ground, all the potential energy would transform into kinetic energy. So it's safe to say that the kinetic energy will be equal to the potential energy at the beginning. So we can say that the kinetic energy is equal to 9,800 joules. So let's see our choices. And the closest answer is D. Next question. An object with a mass 10 kilograms is dropped from a height 6 meters, assuming that air resistance is negligible. The kinetic energy of the object at the instant just before it hits the ground is most nearly, well, it's very similar to the previous question. We're going to say that the kinetic energy will be equal to the potential energy the object gains. So we can say that the kinetic energy in this case is going to be equal to the potential energy. And we already know that potential energy is calculated using mgh. We have the mass, and we have the gravitational acceleration, and we have the height. So the answer is clearly 120 joules. It's the closest answer. Next question. If a person slowly raises a block weighing 100 newtons from the floor at rest to a height of 3 meters, the work done against the gravity is most nearly, and we have these choices. Okay, so he's asking me to find the work done on the object. Well, the work done on the object can also mean the energy used to lift this object. So we can either work it using the work equation, and we know that the work is equal to the force multiplied by the distance, or we can even use the energy equation. But what type of energy is it gaining since we are raising it upwards? Well, it's containing potential energy, which is equal to mgh. Okay, so force multiplied by distance or mg multiplied by h. Well, actually, they're the same thing exactly, because mg is the equation that we use to find the weight, and the weight is m multiplied by g. So we can say that another equation for the potential energy is w, which is the weight, multiplied by h, which is the height. Well, weight is a shape of force and height is a shape of distance. So this equation is exactly similar to this equation. So we can just say that the work or the potential energy, doesn't mind, is 100, which is the force needed to lift a 100 Newton object, multiplied by the height it was raised. So we can say that the work or the energy done is 300 joules. Next question, which graph best represents the relationship between the elastic potential energy stored in a spring and its elongation from equilibrium? Well, this is a very important question. Now, let's look at these relationships one by one. We have here a linear relationship, we have an increasing curve, we have a decreasing curve, and we have a constant relationship. Well, the first thing that may come to mind is the more I stretch the spring, the more potential energy I'm storing in it, so it must be linear. Well, that's not very accurate. Why? Because we know that the potential energy or the elastic potential energy is equal to half k x squared, okay? And x here is the elongation, and here PE is the potential energy. Now he's asking about the relationship between the elongation and the potential energy. We can see that x here is squared, so it's not a linear relationship. This means that A is excluded, so we have B, C, and D. Well, sure, it's not constant. This means that this relationship here means that no matter how much you stretch the spring, the potential energy will be the same. And this is wrong. See, because here I'm stretching, I'm increasing the elongation, but I'm always getting the same potential energy. This one is wrong. So it may be an increasing curve or a decreasing curve. Well, for sure, the more I pull, the more potential energy I'm storing. So it's clear that the answer here is B. Next question. Questions 8 and 9. A strength testing device is sketched to the right. A large hammer is used to strike the lever at point A, driving the 5-kilogram rider up a wire to strike the ball. So, simply, we have here something called a rider, which is a piece of metal that has a mass of 5 kilograms. Now, this is an indication of how high it's above the ground. We have 1, 2, 3, 4, and finally the highest point is at 5 meters. Now, it's asking me the work that must be done to lift the rider high enough just to touch the ball is most nearly. Well, we said the work, we can either use the work equation or we can use the energy equation, or the proper energy equation? Well, since we are lifting the rider above the ground, this means that we are gaining potential energy. So we can simply say that the potential energy that is needed to lift the ball just high enough to touch the bell. So this means I need to rise it up at a distance of 5 meters. So I'm going to say it's equal to mgh. The mass of the ball is already given, or sorry, the mass of the rider is 5 kilograms multiplied by the gravitational acceleration, which is 9.8, multiplied by how high do I need it to raise above the ground just to touch the bell, which is 5 meters. And the closest answer in this case is 250 joules. So I would need to act 250 joules on a hammer to hit this pivot to be able to lift this rider a distance of 5 meters high. Well, again, we must neglect all shapes of energy losses such as friction. Now, next question. It's saying that the rider is driven up the wire. It strikes the bell to make a loud sound. Okay, so it's striking the bell to make a loud sound and falls back to its original position. At which of the following positions is the speed of the rider greatest? Well, before we look at the choices, let's just analyze this question a little bit quickly. We know that this rider is going upwards, so it's gaining potential energy while it's going upwards. But at the beginning, it has kinetic energy. So we have kinetic energy, and it's going upwards because it's moving. At a certain point, it will hit this bell, and at this moment, it would have lost all its kinetic energy and gain potential energy. Okay, so this means that the kinetic energy is highest here and the potential energy is highest here. Okay, now as it's going up, it's losing its kinetic energy. So while we're going up, we have less speed because we have less kinetic energy. Now when it hits the bell and comes back, it will start losing its potential energy and start gaining kinetic energy again. So if we ask ourselves, where is the ball fastest? You're going to say either at this point when it's going up or at the same point while it's going down, because kinetic energy is transforming into potential and potential is transforming again into kinetic. But there's a small trick in this question. It says that it strikes the bell to make a loud sound. So we have some energy losses. Some of the energy was lost when the rider hit the bell. So this means that we will have less energy when it's going down than the energy it had when it's going up. So this means that the fastest point the object will be is at location number 1, or at 1 meter high when it's going up, not going down. It will have its highest kinetic energy or the highest speed at the 1 meter mark when it's going up. Next question. A net force of magnitude F accelerates a mass m from a rest point at A to a speed v at B. So simply we have an object here that's at location A, and we have the object at location B. We have a force F that is pushing the mass m, and when it pushes it, it gave it a velocity or a speed. So in other words, this force is transforming into kinetic energy, or this work, which is the force multiplied by distance, it's transforming into kinetic energy, which is equal to half mv squared. Now, it's asking me expressions that are equal to the work done by F, the force, in moving the mass from position A to position B include which of the following? In other words, what types of energy transformations do we have? We have mg multiplied by d. Well, we know that mg multiplied by the distance, or in other words, the height, is the potential energy. Well, it's clear that we have no change in the potential energy here because the object is not being raised above the ground. So this equation does not do us any good. Now, F multiplied by d, well, this is the equation we use to find the work. And work is the force multiplied by distance. And we already know that, yes, we can use this equation to calculate the work done on the object. And this equation is half mv squared. It's saying that I can use the velocity the object has now to calculate how much energy it gained. So the answer, or the correct answer, would be equation 2 and equation 3. So the answer is C.